Hey AP kids, here's what we've got. This is Unit 1 review. This is what we talked about yesterday. My suggestion is, starting next week, is go through this first, then work through the problems that I will post, because this will give you a review, and then this will help you get through, hopefully, the AP practice problems that I post. So, starting off, I just went through and did each section of the AP curriculum, and so this will hopefully give us some practice problems, some review, some vocab, and get us there. Alright, so we're going to start off. 1.1 is moles and molar mass. Hopefully we remember this fairly simply, and it's pretty easy. So we're going to start with the molar mass of aluminum nitrate. Our first step is to figure out our formula for aluminum nitrate. Remember, aluminum is Al, and we've got nitrate, which is NO3. Al, aluminum, is +3, nitrate is -1. So we have to do our crisscross or get our charges to balance, either way, however you want to think of it. So we end up having 3 NO3s there, and I'm going to erase these charges so they're not there later. And when we find molar mass, if you remember real quickly, we take Al, we have 1 times 26.98. You'll want your periodic table for this, so we got 26.98. We have N, we have 3 N's, because remember, it's distributive. 14.01 is what I think it says on your periodic table. And so that's going to give us 42.03. That is not a 2. And then for O, we have 9 of those. 3 times 3 is 9, so we have 9 times 16.00. And that'll give us 144. And remember, we just add all these up, and that'll be our answer. And that's a very, very quick review on how we find molar mass, 213.01. And our label is grams per mole, most often. Alright, but remember, these are technically AMUs, or atomic mass units. And we'll kind of hit that a little bit later, but that's just something good to remember. Okay, so as we go through, another part of this was conversions to moles and formula units or particles. And so that next question says, how many formula units are in 123 grams of aluminum nitrate? So we can make a little T-chart. We've got 123 grams of aluminum nitrate. All right, put it on our T-chart. All right. 1 mole of AlNO3 or NO3 on bottom, and we're going to put that 213.01 grams on bottom. That way our grams cancel. And then our last step is we'll put 1 mole of AlNO3. And on top, we're going to put Avogadro's number, 6.02 times 10 to the 23rd. And this is formula units. And then we just do our math. Remember, typing this in, hopefully we do it correctly, but we take 123 times 6.02. And remember, we're using that E button, all right? And then divide by 213.01. If we keep sig figs, there are 3 there, so our answer will have 3. So we've got 3.48 times 10 to the 23rd. It should say times 10 to the 23rd or e to the 23rd at the end. And remember, our label is formula units. And that was a quick review there of that one. Alright, everybody down with that? Hopefully that's good review for us. Now, kind of taking it a step further, that like AP likes to do, is it says how many atoms of nitrogen are in those 123 grams. So what we found up here was we found formula units. So that's like how many units of AlNO3 there are. So we can either set up that same thing, or we could use that number, 3.48 times 10 to the 23rd, and that's formula units. And we know for every formula unit, almost abbreviated it. All right, for every formula unit, how many nitrogens are there? Well, there are 3, because our formula is AlNO3 3, right? We have 3, so we're going to say 3 moles of nitrogen. So if we multiply that number by 3, that would be how many atoms there are, which gives us 1.04 times 10 to the 24th, and that's atoms of N. All right, makes sense how we got there. All right, cool, awesome. Rolling on to 1.2. This is mass spectroscopy of elements. So this is where we can find their average atomic mass, or we can identify the element. Just a couple to look at here. We have zirconium, right? And zirconium's official molar mass is 91.224, right in here, right? And that makes sense that we're closer there because the bulk of it is over here, right? If we look at rubidium, now, a question that they could ask for average atomic mass is they could say, well, what is the average atomic mass of rubidium? This is rubidium here. Sorry, it's a little blurry. But we've got rubidium there, so we know it's going to be, because this line, get my highlighter going, this line is taller than this line. We know it's going to be closer to 85 than to 87, but it is going to be larger than 85, right? And if we look at rubidium, it's 85.4678. Make sense? Awesome. Okay, now let's see if we can't plug this into our calculation here. Now we have the average the mass spectrum of europium, and we're supposed to determine the average or the atomic mass of europium. Sorry about that. That should be an of. All right. So we know it's somewhere between 151 and 153. And what do we know? We know it's probably going to be closer to 153. All right? Because it is, we have a larger peak here. All right? We have a larger peak, right? But still, they're really close. That's like maybe they're pretty close. So it's going to be a touch larger than 151, but if you look at the difference in our peaks, we're going to have them fairly close. So it's probably going to be really, really close to 152 because they're almost even. Does that make sense? And so we could guess, I would guess, right around 152, and that should be enough to suffice. All right, everybody down with that? Cool, rolling on. 1.3 and 1.4 is elemental composition of pure substances and composition of mixtures. This is where we get some vocab. Our law of definite proportions says that, all right, any compound is always going to have the same ratio. All right, the same ratio. So water will always be H2O. There will always be 2 hydrogens for every oxygen. All right, our law of multiple proportions says that we have compounds, but they can have different proportions within them. So like sometimes carbon dioxide or carbon can be with oxygen in the form of carbon dioxide or in the form of carbon monoxide, if that makes sense. So we can have different compounds with different ratios. All right, different ratios. Empirical formula, this is our simplest form of a compound, right? Remember, most reduced form. All right, and then our molecular formula is our full-on formula. This is the actual formula. And then what we did for the next 2 problems is we did an empirical formula one, and then we have a combustion analysis one. So we have, in this question, we have a compound containing nitrogen and oxygen decomposed in the laboratory. It produces 24.5 grams of nitrogen and 70 grams of oxygen. So what I like to do is I like to write out our elements. So we have N and O. We have 24 grams of N. And we have 70 grams of O. Our first step is to find moles. So we do that by dividing by our atomic mass of each. Sorry, my label is wrong. That should be a G. We got 1 mole on top. Same thing for oxygen, except it's 16 and 1 mole. Alright, so 24.5 divided by 14.01, we get 1.7488. And I like to keep 4 decimals here just to make sure, because a lot of times we can get into fractions, especially on free response, so it's important that we do that. And then this one comes out to 4.375. So that's our moles. We know, so that kind of brings us to our ratio if you think about it. So we're going to divide each of them by the smallest one to give us what our ratio officially is. Alright, so that one's going to be 1. And then this is 2.5, and this is a perfect example because now we have a fraction and we have to multiply to get the fraction out. So if we multiply each one by 2 to get the fraction out, that gives us 2 there and 5 there, so our formula is N2O5. Alright, that one's pretty simple. Hopefully we get empirical formula, and hopefully we remember that. Alright, now this one's just a little bit tougher because we have to do an extra step or two. Alright, so make this a little bigger. Hopefully we can fit it all on there. So we have a 0.8009 sample. We got it containing only carbon, hydrogen, and oxygen. So I like to write out what we have. And oxygen. Alright, we know that it produced 1.6004 grams of carbon dioxide, and it produced 0.6551 grams of water. So our first step that we need to do is we need to find grams of carbon and grams of hydrogen. And we do that just by unit analysis or converting, however you want to say it. So divide by the molar mass of carbon dioxide, 44.01. 1 mole on top. And we know that for every mole of carbon dioxide, we have 1 mole of carbon. Let's finish that down on the bottom. Now we have to get to grams for right now. We'll get back to moles in a second, but we have to find O, we have to get to grams. So we're going to say 1 mole of C has a molar mass of 12.01 grams. So now we just calculate that all out. So we're going to take 1.6004 times 12.01, divide by 44.01, and this will be our grams of carbon. So we have 0.4367 grams of carbon. Alright, we're going to do the exact same thing with water. Alright, water's mass is 18.02, 1 mole there, grams of water. That's 1 mole of water. 1 mole of water has 2 moles of hydrogen, and 1 mole of hydrogen has a molar mass of 1.01, and that'll give us our grams of hydrogen. So we got 6.6551 times 2 times 1.01 divided by 18.02. And this gives us 0.07344 grams of hydrogen. So to find oxygen, we can use this beginning number right here and take 0.8009, subtract 0.4367, and subtract 0.07344, and that'll give us our oxygen. And our answer is 0.2908 if we're sticking with sig figs. So that's grams of oxygen. Now we just treat this like an empirical formula problem. Divide by 12.01. Divide by 1.01. Divide by 16. This will give us moles. We're running out of room, but hopefully we'll be okay. So, this bottom one, we got 0.018 0.17. This one we got 0.07271, and then 0.4367 divided by 12.01, and we get 0.036, that is not a 6, 3636. Divide each of them by the smallest one, which looks like this guy right here. Change the color here so we can see. That's going to be 1. That's going to be 2. And that one's going to be, you guys are getting there faster than I am, I know, 4. So our empirical formula, C2H4O1. Whew, that was kind of lengthy, but hopefully you're still on track. Maybe you could take a break. All right. Now, 1.5 is atomic structure and electron configuration, and we bring back our favorite guy, Coulomb. All right. What does Coulomb's law say? All right, so we're talking about the attraction, most of the time, well, in this situation, we're talking about the attraction for the protons and the electrons, right? So Coulomb's law says that the greater the charge, the more attractiveness there is, and the less the distance, the greater the attraction is. All right, so hopefully you remember that. Quickly, shells are also called energy levels, right? These are our rows on the periodic table. All right. Subshell sublevels, these are like S, P, D, F, all right? But they're like within an energy level. Our core electrons are our inner electrons, right? These, their job is shielding, right? And then we have our valence electrons, or our outer energy electrons. These are the ones on the outside. These are the ones that are involved in bonding. And then the Aufbau Principle is also called the building up principle. And this is where we build from the inside out. All right, so we start at 1s and then work our way there. I don't know why that is superscript, but we'll make it there. All right, so let's just try one of these electron configurations. We have selenium. All right, selenium is Se. We find it on our periodic table. Its atomic number is 34. So for the full-on one, we've got to start at hydrogen and work our way. So we have 1s2. Remember, s's hold 2 electrons. Then we go to the second row, 2s2. That takes us through beryllium. And then we have 2p6. That takes us through neon. 3s2, 3p6. That takes us through argon. Now we're in the row that selenium is in, so we're going to say 4s2. That takes us through calcium. Then remember we have our Ds, 3d10. So S's can hold 2, P's can hold 6, D's can hold 10, F's can hold 14, and then 4p, and if we count in our P's, we've got 4 right there, so we're going to say 4p4. And that's the full-on electron configuration of selenium. To do the shorthand method of selenium, we're just going to go bracket and the noble gas prior to it, which is argon. And then that takes the place of all of this up here. So then we just end it with 4s2, 3d10, 4p4. So now a variation that we've seen, we saw it in a test question earlier this year. Remember it said only the valence shell, which would just be the 4s2, 4p4. So that's if it's talking about only the valence shell. Because remember, the third energy level is one shell less. Okay? Awesome.